The explosion at LC-36 destroyed Blue Origin's transporter Erector, the only piece of ground support equipment that moved New Glenn to the pad and stood it upright. Most people's first instinct, they have to rebuild it. But Blue Origin just confirmed they won't. And the reason isn't cost, it isn't schedule. In their official update, they said it plainly. We had already been working for some time on eliminating our transporter Erector. They wanted to remove it before the explosion ever happened. The incident just forced them to execute sooner. What I find genuinely interesting isn't the decision itself, it's the question behind it. If they already knew there was a better way, why didn't they move sooner? The answer reveals something very real about how engineering decisions actually get made. Not just at Blue Origin, everywhere. There's one line in Blue Origin's update that most analyses have misread. They read it as a pad recovery decision. It's actually an operations philosophy decision. Blue Origin confirmed they will not rebuild the transporter Erector. The replacement is an alternative vertical Conop, an entirely new vertical operations architecture. And the sentence that follows is the most important one. We had already been working for some time on eliminating our transporter Erector. Read that again carefully. Not we decided to eliminate, not we are evaluating alternatives. Already working. For some time. This decision existed before the explosion. The explosion didn't create it. The explosion removed the last barrier preventing execution. That barrier has a specific name in engineering. Operational inertia, protected by the sunk cost of a certified system. The transporter Erector at LC-36 wasn't just hardware. It was a system that had cleared the FAA licensing process. That meant the entire ground crew was certified on it. Every failure mode was documented. Every procedure existed. Insurance and liability frameworks were built around it. Replacing a certified system isn't a pure engineering call. It triggers recertification, retraining, and a gap where you have nothing to fly, while the old system is still operational. That's why organizations don't replace working systems even when they know something better exists. Not because they can't see the problem, but because the transition cost. While operational is always higher than the transition cost, while standing down. May 29th forced Blue Origin into a stand down. And standing down, as painful as it is the only window where transition cost stops being a barrier. This pattern has clear precedent in aerospace. After Columbia in 2003, NASA didn't just fix the foam insulation. They redesigned the entire external tank attachment and inspection protocol. Improvements that had been known to be suboptimal for years, but never addressed because shuttle was still flying. Standing down created the window to fix what operational pressure had blocked. Blue Origin is in that window right now. 3 vertical Conop architectures and their trade-offs. Blue Origin hasn't released technical details on the new system, but alternative vertical Conop is not an infinite solution space. In the current launch industry, 3 architectures are operating at orbital scale. Each has clear trade-offs. Architecture 1, Mobile Launcher Platform with Crawler. This is the NASA SLS/Artemis approach. The vehicle is vertically integrated at the VAB. The full stack then rolls out to the pad on a mobile launcher platform. Core trade-off. Integration workflow is completely decoupled from the pad. The pad is ready to receive the next vehicle while the current one is still being prepped. In theory, this is the highest cadence architecture. But the MLP and crawler are systems with complexity equal to, or greater than, the TE you just eliminated. You don't eliminate complexity, you redistribute it. SLS takes months between launches, partly because of MLP operations. If Blue Origin pursues this path, they need to out-execute NASA by a significant margin to capture the cadence benefit. Architecture 2. Fixed infrastructure with vertical lift. SpaceX Starship and Mechazilla are the clearest current implementation. Instead of moving the vehicle to the pad, all lifting and erection is handled by fixed tower infrastructure at the pad. Core trade-off. Mobile mechanical systems are eliminated, reducing failure modes tied to vehicle transport. But the entire lifting capability is now embedded in the pad infrastructure. When the tower has an issue, the pad is fully down. SpaceX went through a painful learning curve with Mechazilla in early development. Integrated Flight Test 1 damaged the pad, partly because the ground support infrastructure wasn't yet robust enough. Fixed infrastructure requires higher upfront engineering investment, but long-term, fewer moving parts. Architecture. 3. Simplified vertical transport. This is the least documented approach, but arguably the one Blue Origin is moving toward, given the context. The vehicle is still transported horizontally from the integration facility to a position near the pad, but instead of a complex TE with a full erection mechanism, a simpler fixed crane or lift system at the pad completes vertical erection. ULA uses a variant of this with Vulcan. The vehicle is horizontally transported on a rail system, then erected using fixed pad infrastructure. Core trade-off. Transport vehicle complexity drops significantly, but the integration workflow needs to be redesigned to accommodate the new lift points. Informed prediction. Based on 3 factors, already working on it for some time, implying significant prior investment, a stated commitment to fly before year-end, and LC-36's existing infrastructure, Blue Origin is most likely implementing a variant of Architecture 3, adapted to the LC-36 footprint. Architecture 1 requires crawler infrastructure that doesn't exist at LC-36. Architecture 2 requires tower redesign that's too extensive for the timeline. Architecture 3 can be retrofitted into existing pad structure with more focused modifications. When Blue Origin releases details, that's the framework to evaluate the announcement against. Why holding 7 times 2 is a harder call than jumping to 9 times 4. The decision to hold the 7x2 engine configuration has been underanalyzed in most post-incident commentary. Most coverage reads it as a conservative choice. That framing undersells the complexity. The pressure to jump to 9x4 right now is real. Amazon Kuiper needs launch cadence. Blue Origin needs to demonstrate competitive payload capacity against Falcon 9 Heavy. And if you're rebuilding ground ops from scratch anyway, the argument for going straight to 9x4 sounds entirely reasonable. But here's the specific engineering problem with that argument: confounded variables. Blue Origin is executing 2 major changes simultaneously. 1, a new ground ops architecture that has not been flight-proven at LC-36. 2, return to flight after an anomaly where root cause investigation is still ongoing. In that environment, adding a third change, 9 times 4, with corresponding fluid dynamics, structural loads, and control system differences, creates a system that cannot be debugged if another anomaly occurs. This isn't theoretical. It's the direct lesson from Antares in 2014. Orbital Sciences was in the middle of an engine transition, AJ-26 to RD-181. They decided to fly a mission on AJ-26 while the transition was in progress. A J-26 failure during ascent destroyed the vehicle and caused serious pad damage. Post-incident investigation revealed the turbopump failure mode had been identified during prior testing, but it hadn't been grounded because of the fleet-wide implications of stopping the program. Organizational pressure to maintain schedule overrode engineering judgment on a known risk. Blue Origin is publicly resisting that same pressure. Holding 7 times 2 is a clear signal. They are prioritizing understanding of the new system before adding new complexity. There's one more dimension to this decision that's being overlooked. Blue Origin explicitly stated they are continuing to manufacture 7x2 stages at pace and store them. This isn't keep the plan unchanged. This is a deliberate decision to decouple the manufacturing timeline from the pad recovery timeline. In aerospace supply chains, decoupling is extremely valuable and extremely rare. It requires capital commitment before a launch date is certain. Blue Origin is essentially pre-buying launch readiness. When the pad is ready, they don't enter the sequence of pad ready to wait for hardware to integrate to fly. They enter pad ready to hardware already staged to fly. That's weeks to months removed from the return to flight timeline, paid for upfront rather than waited out. This is the advantage of having a deep-pocketed owner. SpaceX must balance manufacturing investment against cash flow from launches. Blue Origin, backed by Bezos, can absorb the carrying cost of inventory hardware while the pad is being rebuilt. Not every operator has that flexibility. Blue Origin does, and they're using it correctly. The question no one is asking: launch cadence after return to flight. Most LC-36 coverage is asking the wrong questions. When will the pad be ready? When will New Glenn fly again? Those questions are valid. They're just not the most important ones. The most important question is, after return to flight, can Blue Origin sustain cadence? Because that's what determines whether LC-36 is a temporary setback or a genuine inflection point for the program. New Glenn Flight 1 and Flight 2 proved the vehicle can reach orbit. Flight 3 delivered payload, though an upper stage anomaly placed the satellite in the wrong orbit. Flight 4 prep, the hot fire test on May 29th, ended with pad destruction. 4 flights in roughly a year and a half. That's the cadence of a program ramping up, not a program operating at scale. For the Kuiper constellation to be viable, Blue Origin needs a significantly higher launch rate. Amazon's FCC license requires a specific number of operational satellites in orbit before a fixed deadline. Each Kuiper launch carries approximately 45 to 50 satellites. With a constellation requiring thousands of satellites, the math on launch frequency leaves very little slack. This is why the vertical Conop decision, not the pad rebuild timeline, is the most important signal in this entire story. A transporter erector with full certification and maintenance cycles has hard limits on turnaround time. Every TE operation requires pre- and post-operation inspection. The maintenance schedule cannot flex to match Kuiper's cadence requirements. If the new vertical Conop is designed correctly, fewer mobile mechanical components, simplified certification requirements, faster turnaround cycle, Blue Origin isn't just recovering from an explosion, they're building the ground infrastructure for a launch rate the old TE could never support. The explosion, in a very specific sense, may have forced them to build what they needed to build anyway. Here's what I want you to take from this. Not a timeline, not specs, a framework for evaluating whatever Blue Origin announces next. When they release details on the vertical Conop, ask, is that architecture designed for turnaround time or designed for simplicity? When they announce a return to flight date, ask, is the hardware already staged or does the pad become ready before the hardware does? When they release the next launch manifest, ask, what's the inner launch gap compared to pre-incident? Those questions will tell you whether LC-36 was a setback or a reset. There's one final detail in this picture that no one is talking about yet. It connects directly to what the vertical Conop decision has to solve, beyond turnaround time. It's not about speed, it's about an entirely different risk category. One the LC-36 explosion, highlighted in a way that almost no one is framing correctly. That's the full analysis. If this perspective added value, like, share, and subscribe to the Space Brief. Drop a comment below. Which architecture do you think Blue Origin's new vertical Conop will follow? I read all of them. Thanks for analyzing with me today.